Well, welcome. In this video, we're going to be looking at how to identify zeros of polynomial functions and how we can use those zeros to be able to sketch a graph. So let's look at this first example. So anytime we want to identify zeros, zeros is just another name for x-intercepts. So to find the zeros, we're going to set each of these factors equal to 0 and solve them. So including the x, if I just set x equal to 0, I just get x equals 0. If I set x minus 4 equal to 0, and x plus 3 equal to 0, we just simply add 4 to both sides for this one, subtract 3 from both sides for this one, and we get our zeros. So our zeros would be at 0, at positive 4, and at negative 3. Now, we need to figure out, well, what's happening where the graph intersects and hits each of those zeros. So one of the things that we need to know is we need to know the end behavior. Now, if we start out with a polynomial in factored form, to find the end behavior, we have technically, I need to look at this in standard form, but I do not want to take x times x minus 4 times x plus 3. So there's a little trick we can do. And that's just where we take each leading term. Now, if there's an exponent outside of here, we'll see what to do with that here in a little bit. But if there's an exponent outside of there, then we would apply that exponent to that term. But there is no exponent for each of these terms. And so we would have that first factor, we have a term of x. The second factor, we have a term of x. And the third factor, we have a term of x. If you multiply those together, we get x cubed. So if we were to write this in standard form, the leading term would just be an x cubed. So now we can use that to find the end behavior. So remember, we talked about that at the beginning of this chapter. So if the leading term is positive, the right side of the graph goes up. If the leading term is negative, the right side of the graph is down. And then we look at the degree of the polynomial. The degree of the polynomial is odd. And so if it's odd, it goes in the opposite direction. If it's even, it goes in the same direction. So that's how we identify the end behavior. So I know the right side of the graph is going to go up. Now it's not going to go straight up, so we go up and to the right. The left side is going to go down. It's not going to go straight down, but it goes down and to the left. And then we can connect them however you want to connect them, but it would be a wavy line like that. Right? What if it's not in standard form? I'm sorry, what if it's in standard form and not in factored form? Well, then we got to factor it down, because again, we want to be able to find the x-intercepts. So to find the x-intercepts, we got to look at it in factored form. You might say, Mr. Murphy, this is a cubic. How do I factor a 4x cubed? It's not a quadratic. Well, I do want to look for a greatest common factor first. I always look for a GCF first. So for this one, we see that every term is not only divisible by 4, but they also have an x. So I'm going to factor out a 4x. And when I do that, 4 divided by 4 is 1. And if I factor out an x from x cubed, I get x squared. Next, 4 divided by 4 is 1. If I factor out an x from x squared, I just left with x. And negative 24 divided by 4 is negative 6. So now I have a scenario where my a value is 1. So we're going to bring down the 4x, but then now I just have to find two numbers that multiply together to be negative 6, that add together to be my middle term of 1, and so that would be a positive 3 and a negative 2, because 3 times negative 2 is negative 6, and 3 plus negative 2 is a positive 1. So now if I set each of those equal to 0 and solve them, well, I'm just going to do this. If I set 4x equal to 0 and solve it, I would get x equals 0. If I set x plus 3 equal to 0 and solved it, I'd get negative 3. If I set x minus 2 equal to 0 and solve it, I get positive 2. So those are my x-intercepts. So let's graph those. So 0, negative 3, and positive 2. All right, now we need to figure out, well, what's my end behavior? So my end behavior, it's in standard form originally, 4x cubed. So remember, we're going to have a right and left side of the graph. So again, it's positive, so the right side is going to go up. It's a cubic, so the left side is going to go in the opposite direction. So the right side is going to go up, the left side is going to go down. Again, do not go straight up or straight down, because then it's not a function. So it's got to go at an angle. And then just connect them however you want. but that's how your graph would look. We're going to talk more about what happens with connecting them and different changes that might be taking place when we get to the next box at the bottom of our notes here. All right, now this one here, this is a quartic, x to the fourth minus 81. But this technically, if we have two terms, you want to see, is it a difference of squares? And this is a difference of squares. Remember, let's review. Let me put it in terms of a and b. Difference of squares looks like this. A squared minus b squared factors down to be a plus b, a minus b. You might say, well, this is to the fourth power, not a square. Well, remember, difference of squares just means can we take the square root of each term? And even though we haven't talked about roots specifically yet, what times itself would give me x to the fourth? Well, that would be x squared. So my a value here would be x squared. And what times itself would give me 81? Well, 9 times 9 is 81. So my a value would be x squared, my b value would be 9. So factor down would be x squared plus 9, x squared minus 9. Now, I recognize that this is still a difference of squares. Now, the x squared plus 9, I can't do anything with that. Because if I did, if I tried to, I can't, this is a sum of two squares, and you can't factor a sum of two squares. But a difference of squares, which is what we have next, that factors down to be x plus 3, because the square root of 9 is 3. So we'd have x plus 3, x minus 3. Not x squared, because the square root of x squared would be x. All right, so now if I set each of these equal to 0, now I'm going to talk about the x squared plus 9. If I set that equal to 0, I would subtract 9 from both sides. And if I did that, I'd have the square root of negative 9, which, yes, we can take out an I and make that plus or minus 3i, but that's an imaginary number. That's not going to give us an x-intercept. That does not show up on the x-axis at all. The only numbers that show up on the x-axis are real numbers, and an imaginary number is not a real number. So my zeros for this one would be negative 3 and positive 3. And that's it. So now we got to figure out what's my end behavior. So it's based on the leading term, which is x to the fourth. So this time, again, my a value is positive, so the right side is going to go up. But since it's an even exponent, the left side is going to go in the same direction. So the right side is going to go up, the left side is going to go up. And technically, it would have a x or y-intercept at -1. You might say, how do I know that? Well, that's because if we put 0 in for x, my y value would be at -1. I'm sorry, -81. All right, but that's how we can use that information, how we can use the x-intercepts to sketch a graph. But we want to be more specific. So let's look at the next part of our notes. All right, so this is talking about multiplicity. Look over here on the left. It says, how does multiplicity of a zero affect a graph? Well, multiplicity that term, it's important to understand what that term means. That multiplicity just means how many do we have of each factor? And how many we have is going to determine what the shape is going to be at each of those zeros. So here it says examine the end behavior of each of these graphs. So let's start out with just looking at these three. So I already have these three graphs, and because these are going to be, there's something that each one of these graphs will have in common as far as the zeros. Now let's actually stop there. So all of these have the same zeros. If you look, they're all the same factors. So that's the case for all of these. You might say, but what about the exponent? Well, that just means that we have, because remember, an exponent means that we multiply it times itself that many times. So if we have x minus 1 squared, technically that means that I have x minus 1 times x minus 1 times x plus 2. But each of those would have the same zero. Each of those would have a zero of positive 1. So we don't need to list them out each time like that. So we can just keep it as an exponent. Because again, who wants to write down, when we get down to this one, x minus 1 to the 5th power? Who wants to write that down 5 times when we already know that that 0 is going to be the same for each of those? That 0 is going to be where x is 1. So we only have to list it once. So let's look at how each of these graphs where the multiplicity is odd, let's see what the graphs of those look like. When we look at this graph, and by the way, if you hear the acoustics just changed, I had to move when I was making my video to a different room, and so it's got different acoustics right now, so I apologize for the slight echoey sound it might have. But anyhow, when we look at this graph, this is for the first one, x minus 1 times x plus 2. So if you notice, the graph hits that x-intercept of -2 and +1, and it goes through those points. Let's look at the next one where it's cubed. We're going to x minus 1 cubed, so that's an odd exponent. So it hits that x-intercept, and it goes through that point, and then it comes, there's a slight twist, but it goes through that point here where x is 1 again. It's hard to see, but it does pass through that point. Now let's look at x minus 1 to the 5th. I'm going to erase the other two just so that way we can see that better. So when we look at this one, it hits that x-intercept of -2, and it passes through it. And then when it hits this one here, yes, there's a twist. Even though it looks like there's a bunch of points it might hit, it's still just hitting the x-axis where x is 1 and passing through that point. So anytime we have a odd multiplicity, it's going to pass through that point. Let's go back to our notes. You just noticed there from those graphs was that anytime that there was an odd multiplicity, the graph passes through the x-intercepts or zeros. All right, but you might think, well, isn't that what was always happening? Well, what if the multiplicities are even? And that would be looking at those other three graphs that I didn't highlight here. We're going to look at those now. So let me go back to my graphing screen. Let me select those that are even. So let's start with this x minus 1 squared. So notice how this one, where x is 2, it passes through that one. But at x minus 1, so that's going to be where the 0 is 1, it hits that point and bounces off of it. All right, let's look to see what happens for this one, x minus 1 to the 4th. So again, at x plus 2, where the degree is odd, because we have one of them there, so that's an odd multiplicity. It passes through that point. But the point where the factor we have x is 1 is our x-intercept, it hits that and it bounces off. Same thing is true with this one. So it passes through where x is 2, but then it bounces where x is 1. Let's go back to our notes. So when the multiplicity of a 0 is even, it's going to bounce at that point. So anytime there's an odd multiplicity, and if there's just one of them, that's an odd multiplicity. It passes through that point. If there's an even multiplicity like this one, that we know that it's going to bounce at that 0. So let's look at one last example. We'll do the first one together, and then I'll have you guys do the second one on your own. So anytime there's a factor, so this is a factor, this is a factor, and this is a factor, there's going to be a 0. So and this goes back to kind of what we saw at one of the original problems. But for this one, we would have x equals 0, and the multiplicity is 1, because there's only one of them there. And so then that means it's going to pass through that point. Okay, then we would have where x equals -4. There's also only one of those. So we can say it's got a multiplicity of 1. And what that means is that's an odd multiplicity, so it's going to pass through that point. And where x equals 1, that's got a multiplicity of 4. And so since that 4 is even, it's going to bounce at that spot. Okay. Let's look at, so why don't you guys see if you can't try these on your own. Now remember this one here, x squared plus 9, if I set that equal to 0, we'd get the square root of a negative number. So there's not going to be a 0 at that one. So ignore that first one, but I want you to figure out what's happening with the zeros at x equals 1 and at x equals -2. So figure out what the multiplicity would be and what that would mean for the graph at those zeros. So go ahead, pause this video and hit play when you're ready to check your answer. All right, let's see how you did. So at x equals 1, that's got a multiplicity of 5. And since that's an odd multiplicity, it's going to pass through at that x-intercept. So where x would equal 1, it would pass through that point. And then at x equals -2 for the other 0, that's got a multiplicity, since the exponent is 2, it's got a multiplicity of 2. And since that's even, it's going to bounce at that x-intercept. So that's it. So hopefully that'll be enough to help you be able to do your first part of your assignment. And good luck as you work on that.